Hi everyone, my name is Sayed Ahmed and I will be your TA for this semester for Chem A11. And yes, my name again is Sayed Ahmed, and right here, please note, I hope you can all see me by the way. I put excuse me, I put my email on. So please, everyone, if you have a moment, please take a moment and write down my email address and save it someplace special, someplace you won't lose it. Because please remember, I am the one who is giving you your lab, who's giving you the lab talks. I am the one who's marking some of your lab experiments. I'm going to be marking your lab exam, right? Excuse me, sorry, I'm coming down with a little bit of a cough, right? Sorry about that. So please, if you have any questions, please feel free to contact me. Moreover, besides that point, is my internet seems to be having problems. So I have to apologize, and I'm very deeply, profusely sorry for this. But for some reason, when different people start, texting or opening up their microphones and so on, it causes my Blackboard connection to crash for whatever reason. I'm not entirely sure why it crashes, but it has so many problems. So I've done it twice now. And I've TA'd twice now, and both times we've had this exact same problem. That as students started messaging, as students started talking, it crashed. So in exchange, and I hope this is okay, feel free, like all of my slides will have slide numbers, and feel free that at the end of each lab, and I'll say this again, but at the end of each lab, I'll have you have 2 hours. I'll just be available for you guys, and send me your emails, send me your questions, and I'll email the responses. And maybe we can have like a one-on-one thing with Zoom or something else that seems to work better for me. Um, right. So once again, super super sorry about that, and I hope by now you guys have written down my email. And so let's begin our first lab. So experiment 1: solution preparation from salt to solution. Alright, so I guess let's first talk about the organization of the lab, right? So before any lab begins, you guys are expected to do your pre-lab quizzes. Now, your pre-lab quizzes are done, are available to you, I believe, 3 days before your actual lab. Sorry, excuse me. And so I think it's because it's done 3 days. It's available 3 days before, so you should be able to have ample time to do it and submit. Submit the lab, and so that's due before the lab. Now, during the lab will be broken into 3 parts. There are 3 hours and 3 parts to the lab. So in the first hour, we have our lab talk. We talk about the theory. I go over some of the procedures, some calculations, that kind of stuff, right? And it begins at 10 past the hour. So it begins at 2:10 basically, right? Yes. So that's the first hour. In the second hour, so we'll be done our lab talk. Students, that's you guys, are going to do the Labster virtual lab, right? So I'm pretty sure Dr. Narusha talked to you guys about this, right? And mentioned where to go, how to do it. I will do my very best to help you guys out with the Labster virtual lab, but I honestly recommend someone make a WhatsApp group, a Facebook group, a Discord group, whatever, right? So you guys can talk to each other and help each other out. The reason is because I've never done Labster virtual labs. I haven't even TA'd Labster virtual labs before, so this is my first experience. So I'm learning it as you're learning it, except you're actually doing it, and I'm only hearing you guys ask me questions about, for example, I can't use the analytical balance, what to do, and I don't know how much help I can be. Though whatever I can do, I'm here to help. Right? So that's the second hour. And then the third hour are my TA office hours. So please, if you guys can, feel free to come. Feel free to do whatever you need to do. Right? You have 3 hours to do your Labster virtual labs to get the results. If you don't use it within the 3 hours, I believe you won't be able to access it again. So it has to be within these 3 hours. And for 2 of these hours, the second and the third hour, I will be available to help you guys answer questions, that sort of thing. All right, next up, notebook reports. So each of your notebook reports and post-lab report sheets are due 2 weeks after your lab. So 2 weeks after today, basically, right? And except for the fifth lab. So the fifth lab is due 1 week after, right? And that's the final lab, by the way. The fifth lab is the final lab, and it's due 1 week after. If you have any questions about how you should organize your notebook and these sorts of things, I believe Lab Module 1 has a very detailed account. Just follow the instructions and you'll do great. All right, next up, grading. So, here is a breakdown of your grades, and you can see that you have pre-lab quizzes, you have Labster virtual experiments, you have your post-lab report sheets, right? You have your lab notebook reports, and then finally you have the lab exam, right? And so here's the overall breakdown. Feel free to write it down if you want to, or I mean, this lecture will be recorded, or this talk will be recorded, so you can just feel free to come back to it too. But I don't know, by the way, how long Blackboard keeps their recordings. Last time it deleted it after like a week or two. So if you're interested in this, please make a note of it, or just ask me later on, and I'll be happy to help you. Right, whatever works out for you. All right, so without further ado, let's begin. So learning objectives for this lab. So there are 5 learning objectives for this lab. The first is to understand the energetics of solution formation. Basically the enthalpy and how the enthalpies interact and why, right? And what's going on with that. The second one is to prepare an aqueous solution of salt with specific concentrations. So we're going to talk about how to create a particular concentration of a solution, an aqueous solution. And we'll talk about more about what an aqueous solution is later, but basically it means a water-based solution, or where water is the solvent. Thirdly, the third one is to learn the proper usage of an analytical balance. This, I guess, will be done more in the Labster virtual lab, because we're not really going to talk about it here, but I guess the most important thing to note is that you have more digits and therefore higher significant figures, and you can kind of work with that. Number 4, right, to understand and practice quantitative transfer of solids. So once again, I think this is something you're going to learn practically in the virtual lab, and so of course feel free to ask me if you need any hands with anything. I can't really see what's happening in it, but I'm sure if you have any questions on what is quantitative transfer, I can help you out with that. And number 5, practice calculating concentration of solution. So just overall, like if you were asked to make a 0.1 molar solution of sodium chloride, how would you do that? That kind of stuff. All right, introduction to solutions. So a solution, which I've abbreviated here as SOL''N, which I think is a fairly common abbreviation, though I'm not sure what Professor Narusha generally uses in her labs, but I hope that's reasonable enough. So I'm going to use it fairly frequently in my talk. Right, and basically a solution is a homogeneous mixture of 2 or more substances, right? And we'll talk about the different types of possible solutions that can be made later on as well, right? And excuse me. The property of a solution is based on the amount of solute in the solvent, right? So a solute is the amount of stuff you're putting into the solvent. So for example, I'm a big fan of powdered drinks and stuff. So you add like the teaspoons of the powder into water, shake it up, and you can drink from it. So I'm a big fan of iced tea. So in that case, so let's say I was making a big thing of iced tea, right? And so I'd have like a jug of water, and I'd add I think it's like 6 tablespoons in there. Right? So the water is the solvent, and the solute is the is like the sugar or the iced tea or the powder or whatever, right? So basically, the solute dissolves in the solvent, right? And the units for measuring the concentration are generally molarity, molality, parts by mass, parts by volume, mole fraction, and mole percent. And we'll go over all of these in a little bit of detail and with a practical example towards the end of the talk. All right, so how do you describe a solution? So there are two very, I guess, qualitative ways to kind of describe a solution. One is to say it's dilute, which basically means that there's a relatively low concentration of solute, and the other is concentrated solution, right? Which means a high concentration of solute. So, for example, if I make the iced tea too strong, it's too concentrated, right? But if I don't add enough, then it's too dilute. Right, so that's basically how it goes. All right, types of solutions. So now there's a couple different types of solutions. In fact, 5 types of solutions, and some of them are not intuitive. Like, it's not what I would think of anyways when I think of a solution. So anyways, there are the common types. So for example, a solid liquid solution. So for example, me pouring my powder of iced tea into water and shaking it, right? So that's solid liquid, right? There's also liquid liquid. So for example, ethanol and water, right? You can mix them and they form a solution. You can also get a gas and liquid solution, right? So, okay, here's an interesting thing. We generally think of, like, when you open up the tap, you take out water, that it's just water in there, right? But that's not necessarily true. So I am an electrochemist, right? So in our lab, we do a lot of electrochemistry, and oxygen is, because it's a very electronegative atom, is very reactive. So if we try and use just like normal water in our experiments, we always get a huge oxygen peak, because oxygen readily dissolves into the solution, and then it's tough to get rid of. So before we do anything, we have to first bubble out the gases. Well, particularly oxygen gas, we use nitrogen. So we bubble out the gases from the solution, and then we can use it. So almost all liquids, if you leave them out, they're going to have carbon dioxide and oxygen just kind of, and nitrogen too, kind of just float in to the liquid. Again, Le Chatelier's principle will govern, how much goes in. Right? All right. The fourth one is something that I particularly never usually think of when I hear the word solution, but it is. It's a solid solution. So, for example, think of metals. You know how, like, steel is made up of iron and copper and zinc and some other weird stuff, right? Well, not weird stuff. Other elements. Sorry. So it's basically a solution of different types of solids. Right? And then you can, of course, have gas solutions. And I think a simple example of that is, the gases in the atmosphere, or even what we're breathing in right now. It's nitrogen, it's hydrogen, it's oxygen, it's carbon dioxide. Right? So it's gas kind of solution. So it's interesting, I think the first two we intuitively think of as solutions, but also the other 3 are also solutions. So pretty interesting, I think. All right. So, an aqueous solution. So you're going to hear this quite frequently, and aqueous solutions are very, very important, especially if you go into the biological direction, right? So aqueous solution basically just means water is the solvent. Water is the thing in which you're dissolving other stuff into. So, for example, you make sodium chloride solution, and you dissolve a certain amount of sodium chloride into water, right? That's an aqueous solution of sodium chloride, right? Now, what happens when sodium chloride dissolves? Well, solubility is the okay, so what is solubility? So solubility is the property of when a solute dissolves in a given amount of solvent. So just because something does dissolve into a solvent doesn't mean it's going to dissolve regardless of the quantity. So a simple example I think that we can see in our practical lives is when you're adding sugar or salt to, well, hopefully sugar in your juice, right? So if you're making juice and you're adding sugar into it, right, you can understand 2 liters of water, 4 tablespoons, or even 2 tablespoons is not that big a deal. Or even 4 tablespoons is not a big deal, right? It'll dissolve without too much problems. But if you only have like a milliliter of water and you add 4 tablespoons of salt into it, it's not going to dissolve, right? It's going to, there's not enough water for the sugar to dissolve in. right? And there's a certain amount that's required, and that's the solubility. So generally, most compounds, you can look up their solubility online, and it tells you what the maximum concentration is. And of course, that concentration is before superheating. And as we know that, if you were to heat a substance, like let's say you have something and it's not dissolving, you heat it up, it usually dissolves, right? That's superheating the solution, or super saturating the solution, right? Not superheating, it's super saturating the solution, and then you can go. But if you don't heat it up and the maximum amount it can take, it's called being saturated, right? And that's when when you've reached the maximum solubility of a solute in a particular solvent, or a particular amount of solvent. All right. So, what about solubility? What does it depend on? What is it? So, solubility depends on the substance's tendency to mix, entropy, and intermolecular forces. So, we're not going to talk too much about entropy. It's a little bit more of a complicated subject. You're going to touch on it later on as you study in your chemistry careers. But let's talk about the intermolecular forces. So, when intermolecular Okay, so in order for something to dissolve, let's kind of conceptualize what's happening. So let's say that I have water, a jug of water, and I have my tablespoon of powder, like juice or whatever, right? So before I do anything, before I mix them, inside the jug of water, the water molecules are hydrogen bonding with each other, right? There's a lot of interactions going on, dipole-dipole interactions, hydrogen bonds, all sorts of fun stuff. Right? In the juice powder, which we're just gonna simply say it's like sugar, or let's say salt, like it's salt, it's sodium chloride. We know we have the lattice as sodium chloride, sodium, right? We have that lattice, so there's an interaction between each of the components. When you mix the two together, in order for them to dissolve, right, the solvent-solute interaction, so the water-salt interaction, has to be stronger than the solute-solute, so the sodium chloride interaction, and stronger than the water-water interaction. Right? Basically, what it means is that the mixture must be more stable than the two components. Right? And maybe it's a little bit clearer when we look at it in a more mathematical sense. Right? And let's talk about enthalpy. So enthalpy is the amount of energy that is the result of certain reactions, right? It's either endothermic, meaning it requires energy, right? Or it's exothermic, in which it gives energy, right? And so when we have solute-solute interactions that are lower, when the solute-solvent interactions are lower than the solute-solute or solvent-solvent interactions, then the solution formation will depend on the overall change in enthalpy, right? What that means is that if the solution is more stable, being two separate entities, like let's say we have I don't want to say oil, but what's something that dissolves very non-readily? But anyway, something that doesn't dissolve so well, right? So if the interactions between that is, I think silver chloride doesn't dissolve. So let's say silver chloride, right? It's ionic, but it still doesn't dissolve, right? So if the solute interactions are strong, then you won't get solubility. But if the solute-solute interactions are weak, like in sodium chloride, even though it's strong, but it's stronger in the solute-solvent interactions, then you're going to get the solution. So, in a more mathematical sense, the enthalpy of solution is given by the symbol delta and then subscript solution H. Right? And negative means it's going to go on. A negative delta H means that the reaction is exothermic. And if it's exothermic, there's plenty of energy for the reaction. So much so that it's giving away energy. Right? So that's how good or how likely it is. The word spontaneous is actually, I think, technically misused in this slide. So spontaneous refers to something happening by itself. Like, for example, if you were to put a tablespoon of sugar inside 2 liters of water, the sugar will dissolve into the water readily by itself. You don't have to do anything, just put it in and just walk away, and it just happens. Right? Then there are other things that until you heat it, or do something, it won't dissolve. So if it's negative, it'll happen by itself. That's kind of the point I'm trying to make. Right? So if the delta H of solution is way larger than 0, or is just larger than 0, then the solution may still form if and only if the overall delta H has something better, right? So let's say that, so here's the equation, the overall equation. The enthalpy of solution is equal to the enthalpy of breaking the solute-solute interactions plus the enthalpy of breaking the solvent-solvent interactions plus the enthalpy of the solute-solvent interactions, right? Basically, in order to get something to dissolve, you have to first break the bonds between the solutes and break the bonds between the solvents, and then you have to form the bonds between the solute and the solvent, right? And if the overall reaction overall, right, is negative, we're good to go. If it's close to negative, like if it's 0 or if it's and I think I have that on the next slide. If it's 0 or if it's very small positive value, then the solution can still form, right? But very large positive values, the solution won't form. Like the enthalpy requires too much energy in order for it to form, right? But again, energy can be provided, right? You can heat stuff up and you can saturate things. But it won't happen by itself. Like you can't just leave it and expect it to do at room temperature. You have to put in some form of energy for it to work. All right. Now, what if the delta, the enthalpy of solution is 0? Well, if it's 0, then any increase in entropy will drive the solution formation, because if it's even slightly negative, it means it's going in the solution direction, right? And if the enthalpy of solution is 0, is less than 0, it's already negative. So then you have the entropy driving the solution formation, and you have the enthalpy driving the solution formation. By the way, maybe I can give you like a slight description of enthalpy. I'm sure you guys will study this in more detail. Enthalpy can be thought of as the amount of disorder, right? Like when you look at like a lattice structure of sodium chloride, it's like very ordered, right? It's like a cube, right? And then when you put it into solution, then they're everywhere. So enthalpy is the amount of disorder. Whatever is more disorder is more likely, it has higher entropy, in a very, very general sense, just kind of to give you guys an idea of what's going on. So solutions are always have increase the entropy. They always increase entropy, right? But we need to see what happens with the enthalpy. All right. Next up, heat of hydration. So we talked a little bit about the equation here before, right? And so the heat of hydration, delta hydration H, heat of hydration, is equal to the enthalpy of breaking the solvent-solvent interactions plus the enthalpy of the solute-solvent interactions, right? So basically, you can think of it as this way. If the heat of hydration is less than 0, then it's exothermic, right? And for ionic compounds, it's way less than 0. It's not just less than 0, it's like hugely negative, right? And so it very readily happens. But if the solute enthalpy of breaking the solute-solute interactions is lower than what you get in the overall enthalpy of hydration, then again you get exothermic, but you don't necessarily get the reaction to form, and then you have to see about the entropy. But it's a good sign. It's exothermic, so it's likely to happen. And finally, if the enthalpy of breaking the solute-solute interactions is greater than the enthalpy of hydration, then the reaction is endothermic, and you're going to need to put in energy. Okay, so here I have an equation here. So this equation is basically, if you take the heat of hydration, and you say that this is equal to delta solvent H plus delta mix H, and we sub it into the previous equation here. Yeah, previous equation here. So we got delta solution H and delta mix H. Then you end up with the enthalpy of solution is equal to the enthalpy of the solute interactions plus the enthalpy of the heat of hydration. Right? And as long as this is negative, you're good to go. Right? So just make sure that if this is, basically this is a good summary, I think. All right, next up, pre-lab questions. So the first question, and I don't have the exact questions, I have something very similar. So I think these are what you guys were given, right? And I'm not going to go over these exact questions. I'm going to go over something very similar to these questions. All right. So the first one is along the lines of a solution is prepared by dissolving a certain amount of grams of glucose in water. Perhaps the person's making juice. Right? And the final volume of the solution is 617 milliliters. Right? And they want you to calculate a couple things. They want you to calculate the mass for the calculate the molarity, the molality, percent by mass, mole fraction, and mole percent. Right? The second question is that explain how you would prepare the following solutions using dry ammonium chloride and water. So just how to prepare these sorts of solutions. Again, I'm not going to answer like these exact questions. I'm going to answer something very, very similar to these questions. And okay, I goofed up. That should be the second one. Sorry, 1 second. Given that much molality, 1 second, sorry. Here we go. Okay, so here we go. Here's a case of, sorry, I think I have the numbers mixed up here. So here's a case where we have a solution is prepared by dissolving 28.4 grams of glucose in 335 grams of water. The final volume of the solution is 378 milliliters. Calculate the molarity, the molality, percent mass, mole fraction, and mole percent. All right, so first things first, we need to know what molarity is if we're going to calculate the molarity. So molarity is the amount of solute in moles divided by the volume of solution in liters, right? The units are very important. Molarity is always moles per liter. Right? So here's what we're going to do. The very first thing is we're given stuff in milliliters and we're given stuff in grams. Right? We need to convert these into liters and moles. So 378 milliliters, that is 0.378 liters. Right? And we know that because there's 1 liter in every 1,000 milliliters. So we use stoichiometry, the best way to do math, right? And to find this out. So 378 milliliters multiplied by 1 liter per 1,000 milliliters. The milliliters cancel. You get 378 divided by 1,000. You get 0.378 liters. Okay? That's pretty good. So we have liters now. Right? Next thing we want to do is we want to take our 28.4 grams of sugar and we want to convert it to moles of sugar. So there's a couple different things here. So they didn't really give us the molar mass of sugar here, but I mean, if you know the chemical formula, you can always find out. If you have a periodic table handy, all you have to do is go to your periodic table, and we know it's C6, so 12.01 times 6, then we know there's 12 hydrogens, so 12.01 times 6 plus 1.01 times 12 plus 15.99 times 6 for oxygen. Right? You add all those together, you get 180.16 grams, right? And that is the molar mass. So the molar mass is the grams per mole, or the amount of mass it takes to make 1 mole, right? So what you do basically is you take the mass and you divide by the molar mass. So you multiply 28.4 grams of sugar multiplied by 1 mole of sugar per 180.16 grams of sugar, and you cancel out the units of grams. Right, and you do the calculation, and you end up at 0.157 something moles of sugar. Now, we're going to calculate the molarity here, which is just moles per liter. So we have the moles of sugar, we have the liters of water, we do the two together, and we get 0.417 moles per liter. Right? So here's an interesting point. Before I move on to molality and how to find molality, why would someone want molality? Why not just stick with molarity? Everyone knows molarity. Everyone loves molarity. Well, the thing is that molarity depends on volume. And the thing about volume is that it changes with temperature. So, for example, literally, cold juice and warm juice have a different concentration if done with molarity. The reason is because, like, if you not freeze, but if you cool down the juice, then you end up, the volume decreases, the liters decrease, right? So you have a higher concentration. But if you heat it up, you increase the volume and you have a lower concentration, right? But at the same time, what if you want to just make the juice, or what if you're interested in making a solution that you want to know how much is in there, not based on temperature, because temperature can change. You want to know how much of what's in there. Then you go on to molality, right? And molality is defined as, it's a little m, so molarity is the big M, molality is the little m, and it is the amount of solute in moles, so same thing as molarity, amount of solute in moles divided by the mass of the solvent in kilograms, right? So in molarity, we divide by the volume of solution in liters, but here in molality, we divide by the mass, and mass doesn't change as we know it with temperature. And so we're good to go. So it'll stay the same even if you have cold juice or warm juice or whatever, right? It's always going to be the same molality. All right, so how do we calculate the molality though? Well, we already have the moles of solute, right? We calculated it above over here, so we're just going to take that and use it forward. And we can find out the kilograms of our solvent. So we know the volume, we know that it's 0.378 liters. And we also know the density of water. Easiest density to memorize. Water is 1 gram per mil or 1 kilogram per liter. Right? It's like the easiest one. And it's just perfectly 1. It's defined as 1. Right? So 0.378 liters in kilograms gives you 0.378 kilograms. Right? And if we carry on our calculation here, and so they used 355, and so they did it, and you just take your mass per volume, and you're good to go. Right? You divide, and you get your answer. Now, for those of us who do mental math, so for example, in exams and things, right, I always try and do like some mental math to see if I punched everything in my calculator correctly. And the reason is because sometimes you just want to double check. And so if you think about it, we have a roughly 1 over 8 moles, and we have roughly 1 over 3 kilograms. So you divide the two, and you get roughly 0.4. Makes about sense. Right? All right, so we've got molality now. But there was a lot of other crazy stuff we were supposed to get. All right, what about percent by mass? So what is percent by mass? I guess it's the first thing we should ask ourselves. So percent by mass is the mass of the solute over, the total mass of the solution times 100%. Just like your grades or anything like that, right? Like, so if you think about it, like how much did you get on your exam? So you got 99 questions right out of 100. So, right? So you take what you got right, divided by what you got wrong, times by 100%, and you get your percentage. And you're an amazing student. 99% is pretty great. Right? So here, we take the mass of our solute over the total mass, multiplied by 100%. So we know the mass of our solute, it's 28.4 grams. The mass of our solution, what is the total mass? Well, the mass of the solution is the mass of the water plus the mass of the sugar. Right? You add the two of them together, and then you get the total mass of solution. And for those of you who are thinking, maybe I'm going a little bit fast, or maybe you want to take a look at it, it's a lot of information kind of crammed into one spot. So this lecture will totally be posted, and although I can't really interact so easily, but you'll definitely get a chance to see it, and you can pause, and you can go over it in your own time. Right? So we have the total mass here. Right, once you have the total mass, we just divide the two. So we take our mass of our solute divided by the total mass of solution times by 100%, and we get 7.41% by mass. Right, and again, you can do some quick checks to see if everything's right. Right, because one way to do that is instead of 28.4, how many, like x times 28 equals 355. Find x, and that's roughly your percentage. Oh, whoops, sorry. Next up, what about mole fraction? That just sounds complicated. So let's go over it. Mole fraction, given by the symbol x, but like an italicized x, it's like a super cool x, right? Is equal to, so super cool x is equal to the amount of solute in moles. So again, moles seems to be a theme here. So just whenever you get stuff in chemistry, you can just convert stuff to moles. It just you can do it, and you'll probably 99% of the time it'll just be what you need to do. Right? So amount of solute in moles, right, divided by the total amount of solute and solvent in moles. So it's literally the fraction of total moles of your solute. So how do you find out fractions? So let's say I ate 3 slices of pizza out of 7. slices of pizza. How do you get the fraction of pizza I took? Well, you take 3 I ate over 7 total. Right? Same concept here. We have the moles of our sugar. We calculated it a long time ago. We're just going to use the same value over and over again. So we have the mole of our sugar, and we calculate the moles of water, right? And we know the molar mass of water, 18.02 grams per mole. If we don't know, we can always, check it up real quick. It's hydrogen is 1.01 and oxygen is 15.99. So 1.01 times 2 plus 15.99. That'll give us 18.02. We're good to go. Right? And you multiply it by 355 grams of water, and you get the moles of water. Then we use supercool X, mole fraction, right, is equal to moles of solute over total moles. And we have to add the 2 moles together to get total moles. Right? You put it in, and you get 0.00794. So very, very small. And it makes sense. I mean, if you look at it, it's like less than 1 over a 19. Right? So, I mean, you'd expect it to be kind of small. Right? Because if you add 19.7 and you add the 0.157 to it, it's still like 19.8, 19.9. It's still pretty much still 19. Right? So if you just do it quickly in your head, it's like way small over something way big. Right? So 0.00794. And of course, you're always going to round to significant figures, which, by the way, is 3 in all of these. Right? So 0.794, it's good to go. Or 7.94 times 10 to the minus 3. That also works, right? Keep significant figures, always. Lastly, what about if you want to calculate mole percent, right? Well, mole percent is pretty easy. If you calculate the mole fraction, just multiply it by 100%. So we calculated the mole fraction to be 0.00794. We multiply it by 100%, and we get 0.794 mole percent. And there we go. We're good to go. And so that's how you calculate each of the different concentrations. Hopefully it's good. If you have any questions, please feel free to email me, and I will go over it with you. And if we need to, we can meet up again and maybe talk over some other platform. I'm really sorry. Blackboard seems to really hate me, so I'm so sorry. All right, though. Next question, which is actually the first question. It's the second question I asked you guys here, but it's the first question there. So. Alright, so explain how you would prepare the following solutions using dry sodium nitrate and water. So we have 125 mils of a 0.1 molar solution of sodium nitrate. Well, we know what molar means. Molar means that moles per liter, right? So we know that the total volume is 125 mils, and we know to convert it to liters because we're smart, right? 0.125 liters. Right? And we know how to get moles from molarity. We know that molarity is just moles divided by liters, right? And it's a ratio, right? So we take the amount of moles to get the amount of moles we have. We take the molarity and multiply it by our total volume, right? And again, stoichiometry, the best way to do math. You take it, so you get 0.1 moles of sodium nitrate per liter, right? Multiplied by 0.125 liters, and then see the units cancel, right, is going to give you the moles of sodium nitrate. Once you have the moles of sodium nitrate, and usually we don't really want to do anything with moles of sodium nitrate. I mean, I don't know about you guys, but I don't know how to add in 0.0125 moles of sodium nitrate. Like, I have no idea how much that is. So let's convert it to grams so that human beings understand what's happening. And so you multiply it by the molar mass of sodium nitrate. Again, just calculate using a periodic table and a calculator. It'll give you 85 grams per mole, right? So you multiply the moles by the molar mass, and you get the amount of mass of sodium nitrate. So in solution, to make the molar solution of 0.1 molar of sodium nitrate of 125 mils, we're going to need to add 1.06 grams of sodium nitrate in 125 mils. I hope that's clear. Once again, kind of went through it. Didn't really. If you guys have any questions, feel free to ask. Second question is, how would you make it if you want to do 0.1 molality of sodium nitrate, and the other one is percent by mass. Right? All right, so let's talk about molality. So we know molality, we talked about it before. It's the amount of solute in moles divided by the mass of solvent in kilograms. So we know that we want 0.1. Same idea, right? Everything is pretty much exactly the same. So we know the molality. We know that moles equals the molality, and so we know that the mole equals 0.5 moles of sodium nitrate over 1 kilogram, right? Because we want to get kilograms because the units of molality are in kilograms. So in order to cancel out, we're going to need kilograms of water. So we take the molality and we'll multiply it by the molar mass of sodium nitrate. That gives us grams of sodium nitrate over grams or kilograms of water, basically, right? And then we know that the total mass of solution is equal to the mass of sodium nitrate plus the mass of water. Remember, in our molality solution, we just need to use mass of solute in moles over mass of solvent in kilograms. Right? So substituting everything in to get mass of water, right? You can calculate that, go through it, and you get a total mass of water of 124 grams. Right? And then you can prepare the solution basically by mixing 101.05 grams of sodium nitrate and 124 grams of distilled water. Right? And that's how you can go. So I hope that was clear. So basically just go through the molality units and just do stoichiometry and you'll be pretty good. So the next one, however, is a little bit tricky because it involves the concept of using percentages. So let's say you want to make 125 grams of a 1% sodium nitrate by mass solution, right? So here's a little bit tougher. So what we have is we have the total mass and we have the percentage of sodium nitrate of that mass. So in order to solve this, we have to understand something. So we have to understand that 1% by mass means 1% by mass means 1.0 grams of sodium nitrate for every 100 grams of solution, right? That's what 1% means. So if this is our amount, so we just multiply this percentage by the total grams that we're looking for, and we get our mass. So we get 1.25 grams of sodium nitrate. Right? Once we have the grams of sodium nitrate, and we know that the total mass is 125, well, we can just simply subtract the two, and we can solve for mass of water, which is 124 grams. I mean, it's not a lot of water. It's not a lot of sodium nitrate. Right? And there you go. And these guys rounded to significant figures, by the way, if you're wondering what happened. Anyway, so once you do this, you end up with the correct answer. So once again, if anyone needs these slides, they will be made available to you. And of course, I'm available to answer any questions by email. So at this point, I think you guys can head off into your virtual lab. And I will be available if you need anything. Thank you very much. So, yeah. So if you need anything, please email.